Cold dark matter theory needs to invoke the existence of a new particle. Modified Newtonian gravity, on the other hand, needs to invoke the existence of new physics. But if we apply quantum physics to gravity, we find out that we can predict the existence of dark matter without new physics or without new particles. Today, I'm going to present an observational prediction that comes from this idea of getting dark matter from quantized gravity. Why do we have this obsession that we must have a new particle? Well, there are actually two good reasons, two pillars of evidence. The cosmic microwave background analysis of the anisotropies that are there and Big Bang nucleosynthesis both limit the fraction of ordinary matter that's in the universe. These are well-established theories, and on the surface of it, you would think that the conclusion is inescapable because baryons and leptons are not weakly interacting. So DM can't be baryonic or leptonic, and there doesn't seem to be any other suitable particle in the periodic table that would enable us to produce something that's suitable for dark matter. So it means that dark matter must be composed of particles beyond the standard model. However, all of this assumes that we are using the true in situ cross-sections for baryon photon oscillation, BAO as it's called, and for the BBN reactions. And also, that, very importantly, that we know the environment under which BBN takes place. You might think that's cut and dried, but we'll continue on and we might talk about it a bit later. So my question is, could the cross-sections for BAO and the CMB analysis be wrong? And I maintain that quantum mechanics, gravitational quantum mechanics, is the elephant in the room. Can we use gravitational quantum mechanics to check the cross-sections? You can. Well, all you need to do is just treat the galaxy just like an atom. The same as you've got electronic states in the atom, you've got a gravitational basis set of gravity states in the well, and you just treat particles in the same sort of way. Why is this significant? Why does that? You should get the same answer as you get from classical physics. But it turns out that some quantum eigenstates in large gravity wells can be very dark and very weakly interacting. So normally we would have a particle in the well like this, and we would, for example, think about its Compton cross-section as using the classical scattering cross-section for Compton scattering. If we do an analysis using quantum mechanics and split this halo particle up into some sort of wave function, then plot all its states on the eigenstate diagram and get an eigenspectral composition for it like this, we find that in many, many cases for particles in the halo, the eigenspectral composition of our little localized Gaussian wave packet has a whole lot of states that are in this dark region of the gravitational eigenstate spectrum. Baryons then that have a high percentage of dark states in their ensembles will have reduced cross-sections and be dark. So the consequence of that is that halos can be simply hydrogen in a dark eigenspectral disguise. Dark matter is more simply explained with quantum physics and standard particle model physics rather than a new particle. So far from being dark matter being a mystery in this scenario, quantum mechanics says that we should actually expect to have some fraction of any halo as being dark. Okay, so what parameters determine the halo darkness, or what fraction is dark? First of all, it's the amount of gas present. Globular clusters have little or no dark matter because they have no gas. All the gas has been turned into stars, and that's just another story. Dwarf spheroidals are similar in many ways to globular clusters, but they have some of the most dark matter dominant things in the universe. The other thing we've got to consider is the proximity to equilibrium. If we have states in a halo that are all down here in the visible region, then those particles are going to be visible and just behave like we see particles on Earth. If, however, there's equilibrium, then the halo can be much darker. Okay, the critical thing here is the gas temperature. How are we going for time? Oh, great. Okay. And gas temperature is the critical thing, because if we're going to assume that the halo is made of ordinary particles, hydrogen, plus all the other stuff like helium and so on, then what's critical is whether you've got ionized hydrogen, atomic hydrogen, or whether you've got molecular hydrogen. So we're going to look at these cases and just see, can we detect dark hydrogen? Well, we categorize halos into 3 effective temperature types. First of all, the giant halos like the Milky Way, the massive elliptical galaxies and so on. And of course, in these, the temperatures are so hot and ionized hydrogen is what dominates. It turns out to be a very, very narrow range of temperatures according to the Sahar equation, where if the halo was in equilibrium, the halo would just consist of ordinary atomic hydrogen. These are things like AGC 114905 and so on. Oop, wrong way. And then lastly, we've got the super cold dwarf galaxies. These galaxies have temperatures so low that the molecular hydrogen phase dominates. Examples like Segway 1 and some others that I'm going to list in a minute. So here's our Sahar equation. You can vary the density a little bit. It doesn't change the positions of where the transitions are. So down here, we've got molecular hydrogen, green fraction. We've got the narrow region in the middle that has ionized hydrogen. And then up the top where we've got, where we've got atomic hydrogen, and then up the top where we've got ionized hydrogen. So these hot, massive structures, when you work out the quantum temperature, and temperatures, we use that temperature in a very, very loose sense because nothing's really in equilibrium. But we see that the temperatures of all these things are way up here in the ionized region, which is kind of what we'd expect. And so we expect these stars, these halos, to consist of protons and electrons. We don't seem at present to have an observational way to measure the dark proton fraction. And getting that is actually a really big task. The only real way to detect this dark hydrogen would be actually go to the interstellar regions. And we don't have a spaceship to do that. However, Voyager has gone almost into that region. And they're finding that the measurement of the proton-electron densities from plasma oscillations point to a higher density than would be expected. So it's kind of going in the right direction, but certainly by no means, I wouldn't really call it proof, but it's just interesting. So here's the narrow temperature band where H1 dominates. The significance of this is, as I said, if you've got an H1 dominant halo, we can measure H1 because we detect the 21 centimetre line. So we expect that an H1 dominant halo won't appear to have any very much dark matter at all, but it'll appear to have a lot of atomic hydrogen. This is what we see in the dark matter-free galaxy, AGC 114905. Someone said that AGC 114905 has so much atomic hydrogen in it, it's as though every dark matter particle was replaced by atomic hydrogen. And also we can see that that happens in the other dwarf galaxies. I'm going to run out of time, so I'm just going to put those up. You can see all the other dark matter deficient galaxies all have temperature, quantum temperatures that lie in this narrow range. Okay, I'll better get going. Okay, so this is what I really want to talk about, cold halos. The significant thing is that in these cold halos, we've got temperatures that correspond to molecular hydrogen. But can we test this? Well, we have some candidates. How do we test it? Well, one thing we can do is we can look for, jump ahead here, we can look for low vibrational transitions. And I've done a quick calculation of the power that you might get at the detector for a dark molecular hydrogen cloud at 500 Kelvin. It turns out that it's very, very low, but maybe it's detectable by JWST. We have to wait and see. And the other thing that we could do is if there is a quasar lying behind one of these H2 rich halos, then we might be able to see the Lyman-Werner lines being scattered. Okay, and again, this looks like it kind of might be doable, but again, you've got to have a halo line behind. And that's my summary, so I shall stop there. Thanks.
I'm confused about the use of the Saha equation in these conditions. Usually Saha equation applies to L2 dense plasmas. The things that control the ionization and balances are typically not the Saha equation, which is an equilibrium. It's like UV flux coming from hot stars and things like that.
Right.
I don't quite understand how it's done by the Saha.
I'm just using that Saha equation to say if the temperature of a halo is this much, then we should have ionized gas or atomic gas or molecular gas. So, I mean, it's a great point. If the Saha equation, so you're saying that the Saha equation doesn't apply when we've...
It applies in very dense plasmas like...
Yeah, but not 10 to the 6, 10 to the 7.
Interstellar spaces, UV flux coming from very gas stars. So
but we can still define a temperature in that situation,
sure.
can't we? Yeah.
But what determines whether the Titan is ionized or neutral
is the UV flux.
You know, that's how
yeah. No, it's a good point. Thank you.